In this video, we're going to take a look at how we will actually go about solving some second order homogeneous linear differential equations, right? And in order to be able to solve them, there's another assumption or requirement that we will have to make about the differential equation. Now, remember, this was one of the general forms of a second order linear differential equation, right? It could look like this. And then we had like a function on this side. Maybe I'll call it g of x or f of x, right? Um, so the first type that we will learn how to solve, there are two important requirements that we have to make. One, it has to be homogeneous. So we're going to make this function on the right-hand side equal to 0. Two, it turns out when your coefficients are not constants, it becomes more challenging to solve. In fact, many of them you end up having to use like power series, so that those fun things from Calc 2, you end up having to use power series when your coefficients aren't constants, right? Or even if they're not constants, they'd have to be of a very, very specific type to get a fairly easy solution, right? So what we're going to solve, we're going to assume that the a's on this side are going to be constants, and then we're going to assume that g of x is identically 0, right? So under the assumptions, right? So under the assumptions that a2 of x, a1 of x, and a0 of x are just constants, right? And that my function on the right-hand side is identically equal to 0, we get something like this. Now, if my coefficients are constants, essentially what I can do is I can get rid of the x's. So they're no longer functions of x, they're just constants. So I can get rid of that part of it, and then get rid of this, put a 0 there, so then the equations look like this. A constant times the second derivative plus a constant times the first derivative plus a constant times the original function is equal to 0, right? So we refer to these now as, so it's kind of a long title, but here we go. So we refer to these as linear second order homogeneous DEs with constant coefficients. Quite the mouthful, right? With constant coefficients. So it seems like we're making a lot of assumptions to kind of simplify the problem, but it turns out those assumptions are justifiable in the sense that a lot of important application, real-world applications that many of you will see in subsequent courses boil down to being able to solve differential equations of this form, right? So it's not just a matter of making it easy so that we have easy work to do, but it also will enable us to utilize equations like this when you get to more advanced applications, right? Okay, so the question is, how could we go about solving something like this? Like, where do we start? You have a function that's unknown. And since you don't know what the original function is, then you don't know what the first derivative is, and you don't know what the second derivative is. But if you look closely at what this is saying I have some function that when I multiply it by a constant, and I multiply its derivative by another constant, and then its second derivative by another constant. And when I add those three things together, I have to get 0. So what this basically means is that uh, if I have whatever type of function my original function is, then its derivative and its second derivative would have to be of a similar type. Otherwise, I wouldn't be able to add them all together and just have them cancel out. So in other words, the first derivative couldn't be like, the original function couldn't be something like a log function. Because if it's a log function, when I differentiate it, I get 1 over x, right? And I mean, unless I'm just going to make all my constants equal to 0, which again, that would trivialize the whole problem, right? There's no way, for instance, I could have a constant times a log function plus another constant times, say, 1 over x, and somehow that cancels out and gives me 0. So what this is implying is that y prime, and y double prime must be of the same type of function. So must be of the same type, right? Well, what do we mean by type? Well, when I say type of a function, I mean something like quadratic, or, a trigonometric, or more specifically, maybe a sine and a cosine function, right? Because they are like, if you think in terms of sine and cosine, then we know that when we differentiate them, they just kind of, they fluctuate, they kind of oscillate between each other. The derivative of sine is cosine, the derivative of cosine is negative sine. So they're relatively the same type. But there's another type of function that no matter how many times we differentiate it, it pretty much stays the same type of function. And that happens to be our basic exponential function. So one function of this type, one function with this property, is the exponential function. So the exponential function, and I'll say y equals, and I'm just going to call it like e to the, now it doesn't have to be just e to the x. Other types of exponentials have it, like if I have a constant in front of the x, right? Then when I differentiate this repeatedly, I'll still have the e to the mx. The only thing that will change because of the chain rule is the constant that's multiplying it, right? So if I say that, okay, my m can be some real number, right? Then again, let's just illustrate this fact that if I differentiate it once, I am going to get me to the mx, right? It's the same type of function, just a slightly different coefficient. If I differentiate it a second time, I'm going to get m squared e to the mx. Again, it's the same type of function. No matter how many times I differentiate my e to the mx, I'll still have e to the mx times some constant, right? So it is plausible to think that this type of function could satisfy this differential equation, right? Well, if this function is supposed to satisfy this differential equation, then if I take the y and y prime and y double prime and substitute it into the left-hand side, then it would have to simplify and give me 0, right? And then maybe that would be a way for me to figure out what m has to be, right? So let's say that. So if y equals e to the mx is going to satisfy this differential equation, so if y equals e to the mx is a solution, right? then this would have to be true, right? I'd have to take this constant, multiply the second derivative. So I will have a2 m squared e to the mx, right? So plugging the second derivative in there, then plug the first derivative in there. So I would have a1 times m e to the mx, and then plug my original it was sort of my guess, right? It was sort of my educated guess, thinking, okay, because of the pattern that I see here in my differential equation, only a certain type of function could possibly satisfy it, right? So I'm going to take my y, which was my original guess, and I'm going to plug it in there. So I'll have plus a sub 0 and then e to the mx. But again, if this function is going to satisfy the differential equation, this whole thing has to be equal to 0. Right? Okay, so now we're kind of making progress, because if you notice what's happened, the terms that involve the x, they're all now exponential. In fact, they're all of the same exponential, so I can actually factor out an e to the mx. So if I factor out an e to the mx, what do we have left? We have a2m squared plus a1 times m plus a sub 0, and then that's equal to 0. So now we're really getting somewhere, because we're saying if this function satisfies my solution, then this equation has to be true. Well, based on what we know about algebra, then it means, since I have it factored, then either e to the mx would have to be equal to 0, or my a2m squared plus a1m plus a sub 0 would have to be equal to 0. And this is a quadratic equation. So I think that's pretty remarkable, because remember, what we're starting with is we're trying to solve a differential equation. And based on the pattern in that differential equation, we kind of made a guess or a hypothesis about what the solution would have to be based on what we know about derivatives. And based on that guess, we've derived these two possible equations. Now, if you think about it closely, this has no solution, right? There's no way an exponential function can be equal to 0, right? So this has no, in fact, I'll just say that this is not possible. Never possible, right? So if we wanted to figure out what the m would have to be in our special solution, then we would have to solve this quadratic equation. And notice what the quadratic equation is. It has the same coefficients that were in the differential equation. It's just that now there are no derivatives in this equation. And this quadratic equation is called the auxiliary or characteristic equation of the differential equation. So this quadratic, right? So this quadratic is called the auxiliary or characteristic equation of my DE, right? So solving that particular type of differential equation comes down to solving this quadratic equation. So let me just kind of summarize what we've done so far, right? So here we have, so this is the type of differential equation that we would like to solve. Right? This second order, linear, homogeneous, constant coefficients, right? And then based on an educated guess, right? So based on the pattern and what we know about derivatives, the only type of function that it seems reasonable, right? At least one type of function that seems like a reasonable choice here would be a function of this form, right? So if this is a solution, then we can figure out what m is by solving this quadratic, this auxiliary equation. Why is it called auxiliary? Well, when something that's auxiliary, something that is helping, something that is kind of supplementary to a bigger thing. Well, in order to solve the differential equation, we have to solve this algebraic equation, right? So this is our dE, and in order to figure out the solutions to this, we have to solve this, and I'll call it an AE, or an algebraic solution, algebraic equation, right? Now that to me is wonderful, because notice that there is no sign that we're going to need to do calculus, right? There's no sign that we'll need to do calculus. So let's take an example. Let's do an example of one of these, right? Just to see what the process would look like. Because right now we're just dealing with a whole bunch of, it's like a whole alphabet soup right here. But let's make it a little bit more concrete. So let's say we have something like this: y double prime minus y prime plus, or actually let's make it minus 2y is equal to 0. So let's say this is my equation now, right? Then the auxiliary equation for this, right? So the auxiliary equation, right? So the auxiliary equation, oh, and I think I see where I misspelled auxiliary up here. It's 1L, not 2 L's. There we go. Got to deal with good grammar here and spelling, right? So the auxiliary equation for this differential equation is, so let's write it down. So my A here, A2 is 1, A1 is -1, and then A0 is -2. So basically it's the exact same coefficients, but we now end up solving a quadratic that looks like this. And the choice of the letter M is a little bit arbitrary. It doesn't have to be M. Sometimes you might see other authors might use R, some might use different letters. But the pattern here is that this differential equation with this observation becomes a quadratic equation that looks like that. So let's see, so that means if we can solve this, we can figure out what M is, and that should give us, well, in fact, when we solve the quadratic, it's possible that we get two solutions. So maybe we'll get two special functions that will work, right? So if we factor this factors as m minus 2, and then m plus 1, that's equal to 0. So we have two solutions. So I'll write it like this: m1 is equal to 2, or m1 is equal to -1. So then the question is, would these numbers really work, right? So this implies that we basically have two solutions. Either y is equal to e to the 2x, or y is equal to e to the -x. Right? Let's get this off. Wait, what's up with my eraser? There we go. So y equals e to the -x. So in fact, let me call this, oh, that should be a 2. So let's make that y1, and let's make that y2. So we have these two functions. Do they really satisfy the differential equation? Let's check and see, right? So if y1 is e to the 2x, then let's take the first derivative. So y1 prime is 2e to the 2x, and then y1 double prime is 4e to the 2x. So let's plug those in here and see, do we actually get 0, right? So let's see, so we'll have our 4e to the 2x minus 2e to the 2x, that's my first derivative, 2e to the 2x, and then minus 2 times my original function, so minus 2e to the 2x. And yes, this all cancels out, because I have 4e to the 2x minus 2e to the 2x minus another 2e to the 2x, so that is 0. So that function does work. Fantastic. Let's see if the other function works. So let's see if our y2 works. So if y2 is equal to e to the negative x, then its first derivative is negative e to the negative x. And then its second derivative is again e to the negative x. So now let's plug these three functions into the left-hand side of my differential equation, and let's see if we get 0. So this implies, so if I take my second derivative, which is e to the negative x, and then minus the first derivative, which is negative e to the negative x, and then minus 2 times my original function, my original y2, that's e to the negative x. So let's see what happens. So I'm subtracting a negative here, so that's addition. So this ends up being 2e to the negative x minus 2e to the negative x, which again is equal to 0. So it does work. Okay, so that's fine. We found two specific functions that work. But when you think about it, when we're solving a differential equation, if we don't have conditions, and right now there are no conditions here, we would typically get a general solution, right? In other words, we will get a general solution that usually has constants that are involved. And it turns out we can do the same using these two special functions. Now, I'm going to do something that seems a little strange, but it's done to emphasize an important theorem that we're going to state in a second, right? So we know that these two functions by themselves, they satisfy the differential equation, right? We verified it right here for y1, and we verified it right here for y2. Now, if you recall, earlier we talked about this concept of a linear combination, right? When we were studying vectors, right, we talked about taking two individual vectors and forming a linear combination of those two vectors. I remember what a linear combination is. It's where you're allowed to multiply, and back then it was vectors, right? One vector by a certain scalar, and then another vector by another scalar, and then you were allowed to multiply them, right? So what we're going to do now is this. Consider the following linear combination of these two functions, the e to the 2x and the e to the negative x. So a linear combination of y1 and y2, right? So what I'm going to do now is I'm going to write down another function which is some constant times e to the 2x plus some other constant times e to the negative x, where I'm just going to say that c1 and c2 can be any real numbers, right? Now I'm going to do something even stranger. I'm going to ask myself, could this linear combination of these two special functions also satisfy the differential equation, right? So would the fact of multiplying each function by constants, right? Would that change the fact that they once satisfied the differential equation? So let's see. Now, does this? So we're going to ask ourselves this question: does this y also satisfy the dE? Well, in order to answer that question, we have to do the same thing that we did right here. We have to find its first derivative and its second derivative, and then we have to plug it into the original differential equation and see if, in fact, everything cancels out and if we get a zero, right? Well, let's write down what the first derivative of this would be. So this will be 2c1 e to the 2x. And then this will be minus c2 e to the negative 2x. Just remember that we have to use our chain rule, right? We have to use our chain rule each time. Second derivative will be now 4c1 e to the 2x, and then plus c2 e to the negative x. Right? And remember what the differential equation says. In fact, let me remind you, the differential equation says that the second derivative minus the first derivative minus 2 times the original must be equal to 0. So let's check it to see if I take this function minus this function minus 2 times this function, will it all cancel out and will I still get 0? Right? So let's see. So here's our second derivative. It's 4c1 e to the 2x plus c2 e to the negative x. And then minus the first derivative, so minus this quantity, 2c1 e to the 2x minus c2 e to the negative x. And then minus 2 times the original function. So minus 2 times the quantity, c1 e to the 2x plus c2 e to the negative x. Let's see how this goes. So we have 4c1 e to the 2x plus c2 e to the negative x. Distribute the negative 1 there. So I'll have minus 2c1 e to the 2x plus c2 e to the negative x minus 2c1 e to the 2x minus 2c2 e to the negative x. Now let's collect the like terms. So let's group everything that has an e to the 2x. So this, and this. And then let's group everything that has an e to the negative x. So this, and this. So let's start with so what I'll do is I'll factor out the e to the 2x. That leaves a 4c1, and then a minus 2c1, and then a minus 2c1. And then factor out the e to the negative x. That leaves a plus c2, and then another c2 plus c2, but then a minus 2 c2. So what happens is these coefficients, these three terms, they simplify to 0. These three terms, they simplify to 0. So we end up getting e to the 2x times 0 plus e to the x times 0. And not only, right, so this is pretty remarkable. This is pretty remarkable that we found two specific functions, right? Our e to the 2x plus e and e to the negative x. We found them separately by solving that quadratic equation, that auxiliary equation. And then we realized that separately they satisfied the dE. But now we formed this linear combination which now represents infinitely many possible functions, because I can have any constant here and any constant here, add them together, right? And it turns out I still have a solution to the differential equation. And that is the power of these linear differential equations, is that once you find two special functions that satisfy the second order dE, you can use linear combinations to find your general solution. So any constant multiple of e to the 2x plus any constant multiple of e to the negative x will be a solution to this differential equation. And there's a very important theorem that tells us when that is possible. All right? So before I state the theorem, I want to go back to another concept that we looked at during linear algebra. It was the idea of linear independence, right? And I'll just do this. So recall two vectors are linearly independent. Remember, one of the easy ways to identify if two vectors are linearly independent is if they're not scalar multiples of each other. So two vectors are linearly independent if and only if they are not scalar multiples of each other. Well, it turns out this same concept of linear independence can be extended to functions, right? So with this in mind, we say two functions are linearly independent if and only if, again, these functions, they are not scalar multiples of each other. Right? So scalar multiples of each other. So that means we can say if like one function is not a constant multiple of another function, then we can say f of x and g of x are linearly independent. And another way of saying this too is that suppose I divided both sides by g. So another way to say this is if f of x divided by g of x is not a constant, right? So if the ratio of two functions is not a constant, then the conclusion is the same. F of x and g of x are linearly independent. And this would be for all x in some interval, right? So I'll just say this, for all x in some interval, right? And the reason why we need this concept now as applied to functions is because it tells us which two functions or what must be true about these two functions in order to use this idea of a linear combination to get my general solution. All right, so now we're ready to state this very, very important theorem. It's a huge theorem, and it actually makes our life a lot easier. You'll see, well, you kind of got a sense of it in that little example, but going forward, we'll be able to use this theorem and get general solutions of these second-order homogeneous linear constant coefficient differential equations very easily. And this theorem is called the superposition principle. You can thank the engineers for that title, engineers and physicists, but the superposition principle. And this is what it says. The general solution of, and I'll write down the equation that we're solving now, that the constant times the second derivative plus the constant times the first derivative plus a constant times the original function equal to 0, right? So this is the type that we're solving. So the general solution of this equation is given by y equals c1 times y1 plus c2 times y2, where y1 and y2 are any linearly independent solutions of this equation. So if I can find two functions that are not scalar multiples of each other that satisfy this differential equation, then all I have to do is take any linear combination of those two functions and I will get my general solution, right? So it's given by this. So where y1 and y2 actually, let's say it like this. So y1 and y2 are linearly independent solutions of the differential equation, right? And this is precisely what we did earlier, right? This is precisely what we did. How did we come up with those two special functions? Well, we solved the auxiliary equation, and we were lucky enough to get two distinct solutions from that quadratic equation, and then we got our y1 and y2. So then the superposition principle just says if I want to find every solution to this differential equation, I simply have to take every any linear combination of those two functions, and that will give me my general solution. All right. All right. So let's wrap up with another example here, just to kind of put this whole process in good stead, right? So here's our example. So let's say we have 2y double prime minus, right? So minus, let's say y prime, and then minus 21 times y, and then that's equal to 0, right? So let's say this is our differential equation, and we want to find the general solution. So our first step is to write down this auxiliary equation, right? So the auxiliary equation, what am I? Okay, so auxiliary equation is, well, again, it's the corresponding quadratic, and we're just using m as our variable. You can use anything. Don't use x, don't use y, but I'm just going to consistently use m. So it's 2m squared minus m minus 21. That's equal to 0. And then our goal is to solve this, to figure out what m can be. Right? Well, what are the possible values of m? Well, if you look closely, this can actually be factored, right? Because what we're looking for is we're looking for factors of a negative 42 that add to give us a negative 1. So we want factors of negative 42 that add to give us a negative 1. Well, if I do negative 7 and a negative 6, right, or a positive 6 actually, that will work, right? Because if I multiply these two, I'll get negative 42, and if I add them, I'll get negative 1. So then we can use that procedure to help us to factor. So I'm gonna put the positive 6m there, and then the minus 7m, and then minus 21 equals 0 there. And then we can factor by grouping, right? So I'm going to group the 2m squared plus 6m, and then I'm going to group the negative 7m minus 21. That's equal to 0. factor out a 2m out of the first pair. So that gives me m plus 3. And then factor out negative 7 out of the second pair. And that also leaves a m plus 3. So I know my process is working. So now factor again, factor out the m plus 3, and then that leaves the quantity 2m minus 7. So here we're going to get our two m's. So m1 is equal to negative 3, and m2 is equal to 7 halves. So what this means now, we found our two functions. So we found y1, it is e to the negative 3x, and then y2 is e to the 7 over 2x. And notice, these two are not scalar multiples of each other. There's no constant that I can multiply e to the negative 3x by and get e to the 7 halves x, right? So these are linearly independent, and that's what we need. And then now the superposition principle says, here's our general solution. So therefore, the general solution is y equals a constant times y1 plus a constant times y2. So we end up with c1 e to the negative 3x, and then plus c2 e to the 7 halves x. And that's our solution. So we've come up with all the possible solutions to this differential equation without ever having to do any kind of calculus, no derivative, no antiderivative, right? But we utilize some important linear algebra concepts, and the big thing was that superposition principle theorem. All right. So I think that that's a lot in this video. Definitely, maybe go back and watch some of the key points, seeing how do we come up with the auxiliary equation. Obviously, the solving part is easy. Identifying the two specific functions are relatively easy. And then again, using that superposition to put it all together to get our general solution. Right? So lots of good stuff. And then we'll continue working on questions that look like this. But then there are some outstanding questions like, what if our quadratic doesn't have two real solutions? What if there's a repeated solution? Or what if the solutions are now complex numbers? How could we possibly get functions out of that? Well, that's the good stuff that's left to come. So tune in to the next video, and I'll see you then.